Hi and welcome to the final inquiry question of Module 7, and we're looking at polymers. Today we're looking at a different type of polymerization. So previously we've been looking at addition polymerization. Today we're looking at condensation polymers. And as we've previously discussed, our condensation polymers are looking at one molecule of water being removed during that process. So in this case, it differs from our addition polymerization because we're not having a double bond that's breaking, allowing that polymerization to take place. But in actual fact, we are having single bonds and a couple of monomer units joining together. And in this case, we're also producing two molecules as opposed to the one where we've got our polymer and that unit of water. So looking at the outcome that we're going to look at or achieve through this video and the next is model and compare the structure similar to what we had before, the properties and the uses, but this time we're looking at condensation polymers and examples here are nylon and polyesters. So let's look at these natural polymers. We talked about these natural polymers right at the beginning, such as cellulose, proteins and so forth. So starch, cellulose and proteins are naturally occurring condensation polymers, and they're made from the reaction between glucose monomers. So where our glucose, as you can see in this diagram here below, our glucose monomer is then repeated over and over again. And so you can see here's that glucose molecule, here's that glucose molecule, and in here you can see there's that water, that linkage there. So our proteins that we have are also made from amino acids, and we often hear of our amino acids within our body and necessary for our body as well, and those repeating units are what make up our proteins, and we'll have a look at these a little bit more detail in class. So cellulose, so our cellulose cell walls and things like that in plants is a polymer. It's made up of that glucose monomer repeated. Now if you actually go back and have a look, you'll see that it is inverted. So you can see the CH2OH is up here, the CH2OH down here. So it's inverted each time it's added there for it to join together. So that is making then, so one's up, one's down, and it's making then one very linear in structure. So if you have a look at that structure, it's still forming a linear, a line type arrangement there. And cellulose is pretty much the major component of our biogas that we would have looked at when we looked at alternative fuels and using biomass as a fuel there. And because of that, it's one of the major structures to build those petrochemicals. But what we're going to look at today is our synthetic condensation polymers. And again, many of these you will have heard of before, and they're produced through the condensation reactions. And polyurethanes, they're used in often coating your floorboards. We use a polyurethane covering on floorboards, adds a nice water tight protective seal. PET plastic, so you'd think of your PET bottles that we often look and recycle. Polycarbonates, again often used in cupboards, and polyurethanes are used in cupboard coatings and so forth, but nylon and polyesters. So we're going to look mainly at the nylon and polyesters through these videos. So the difference between the monomers that we had with our addition reactions and these condensation reactions is they actually don't react at the double bond like we had before, where the double bond was split and that allowed the reaction to continue. But here they actually react where two functional groups come together. So in this case, we actually have two groups coming together, they react, give off a product, and then that is repeated several times. So each one of those monomers though can have a couple of different reactive sites which will improve the branching there, and we can get those side chains. So looking at this one here, which is nylon. Nylon, if you actually have a look, we've got a carboxylic acid here on the end, so dioic acid. Why is it di? There's the carboxylic group here and the carboxylic group at the end. And this one over here, hexane 1,6-diamine. Why is it diamine? Because we've got an amine group on this side and an amine group on this side. So what's happening here is these two, the carboxylic acid reacting with an amine, they're coming together. And you can see at this end of the reaction, if we take the oxygen with the hydrogen, and they can then form, and you'll notice here that we've got our C double bond O, we've got our C to our N, like we have up in here, and we're left with one water molecule has gone and we're left with that hydrogen there. And you can see that this repeats and joins and then repeats again here, and the water is actually removed out. So what are some of the properties of our nylon? Nylon was revolutionary initially when they came about, as we made many things such as stockings, which replaced what was previously silk stockings, and now they're actually made out of nylon. It's thermoplastic, so it tends to melt when it's heated, so it allows it to be shaped and so on. It's strong. Most of your stockings, yes, they can ladder, but the threads themselves are relatively strong. They're elastic, waterproof, and again resistant to attack. Now, that nylon, as I've just said, can be drawn into long wires, and they've got a high tensile strength. So again, while they may rip and whatever else, if you actually pull the nylon strands, they're quite strong, and they're used to make things like clothes. So nylon is much more common now in our clothing. Parachute, fishing line, guitar strings are nylon, and so on. So quite strong, but they can also be used in harder plastics. So we'll have a look at answering a few of these questions in class, as well as providing some extra reading materials for you to plump out your understanding of nylon a little bit further. See you then.